Hi, my name is Derek Larson. I'm an energy engineer with McKinstry in the Spokane, Washington office. And today we're going to be looking at a couple different options for a small-scale renewable energy system that we might install at our building. So let's start with some project background. So we are going to propose either a 10 kW solar array or a wind turbine system. Now the purpose of this is to supplement the existing electric service to our building. With the electric use that we see each year at our building, which is a little over 800,000 kWh per year, this renewable system would only supplement a very small percent of that, but really the point of this system is to support McKinstry's commitment to sustainability, because that's what we're about. We're about saving energy, we're about green construction and energy retrofits, and along those same lines, this would improve McKinstry's brand and image to the community. So looking at some potential locations of where we could put a system like this, if we're looking at a wind turbine, if we're going to put it on the ground, there's really not a lot of space here on our property that's not already taken up by buildings or a parking lot. So if we were going to put it on the ground, we'd have to put it along the west side of the property, right near the Spokane River. But another option could potentially be to place it on the building of the roof. Now with the solar array, the obvious location to keep it the best protected and out of the way would be on the roof, which should be a relatively easy install. So here's a photo of our roof where we could place it. You can see it's nice and clear, shouldn't be any issues there. And one of the examples of the ground location, you can see a nice clearing of grass there. Now let's start to look at some equipment selections. So for our wind turbines, we researched 3 different turbine types. So we have a 10 kW SAWT PK10AB. Now this is a vertical axis wind turbine. The benefit of this turbine is it is expected to come in at the lowest cost, just based on the technology and where it's made. It's made in China. Option 2 would be a 10 kW Berge Excel 10, and this is a horizontal axis turbine which has more of the traditional look that you might expect from a wind turbine. This is more of a premium option. This equipment has by far the best warranty and the best expected equipment life. And the third option we looked at, which is also a horizontal axis turbine, this is the Evancewind R9000. Now for this option we would actually go with 2 5 kW smaller turbines in place of a single larger 10 kW as we would with the other turbines. Now the R9000, the big benefit there is it is expected to have the best performance. So when we're comparing wind turbines, a big thing to look at is the power curve. So what this chart shows us is a correlation between wind speed in meters per second and a rated power output measured in kilowatts. So we've taken all 3 of our turbines and we've superimposed each of their power curves on top of each other. And this gives you a very clear idea of where one turbine is going to excel over the other ones. So if we were looking at a site where we had lower wind speeds, say in the 6 to 10 meters per second range, then clearly the Evancewind R9000 turbines are going to be the best. But if we are in an area with really high wind speeds, where we're seeing a lot of times where we're over 12 meters per second, then one of the other turbines is obviously going to be the best in terms of performance. So for the solar panels, we did something very similar where we looked at 3 different panel types. The first one are the 335 watt sun power panels, and we would require 30 of these to get up to our 10 kW rated output. Now these panels utilize monocrystalline cells, which do give it the best efficiency of the panels we're going to look at, and this manufacturer also offers the best warranty and has the least amount of power degradation over the life of the equipment. The second panel we looked at were the 250 watt gigawatt panels, and we would require 40 of these, so an additional 10 over the SunPower panels. The big difference here is these panels use polycrystalline cells, which are going to be a less efficient but also less expensive option. And these panels are made in the USA, which is kind of a big deal, as we're going to find out as we get into the environmental impact piece. And we also looked at a 250 watt Renesola panel, and this panel also uses polycrystalline cells, and on paper it's effectively identical to the gigawatt panels, but the big difference is these ones are made in China. And again, there is an environmental impact there related to where the panel is made. However, these are expected to come in at the lowest cost, and so that's the big selling point. So let's take a look at our meteorological data. So the power output of each system type is going to be determined by one, what's going on with the wind, and two, what's going on with the solar irradiation. So starting with our wind data, we pulled wind speed data from the MesoWest website, which is a collaboration between the University of Utah and a number of researchers around the country. We pulled 3 years of data, which was largely hourly data, so that was a lot of data points, and that really allows us to get a really clear picture of what we might expect from the wind energy potential in Spokane. And then we took that data and we imported it into an analysis software called Windographer to produce some additional graphs to really paint a clear picture of what's going on at our site. So this is what's called a wind rose, and this is put together by that Windographer software. And what this shows is the overall wind energy potential by direction. So what this is telling us is that the wind energy over a typical year in Spokane is going to really predominantly come from the southwest side of the property. And so what this allows us to do is to look at the property and see if this can help us place our turbines and look for any pitfalls as far as things that might be in the way that will impact our wind system output. So at our site, we do have some trees along the southwest side of the property, but they're only about 10 meters high at most, and our hub height is going to be probably in the 25 meter range, and so I would expect that would be high enough above the trees that it wouldn't be an issue. If we place the turbine on the roof, then there'd be even less chance of those trees causing issues with our wind output. So looking at our average monthly wind speeds, the blue line is the wind speed at a height of 10 meters off the ground, and that is the actual measured data at our mesonet. Now, using Windographer, we can extrapolate that data to a different height. In this case, we extrapolated it up to a expected hub height of 25 meters, and that's the red line you see higher up. And as you can see, as you go up in elevation, your wind speeds also increase. Now, with a typical wind system, it can be useful to try and correlate when you're going to see your peak wind speeds versus when you're going to see your peak building demand. In this case, with our building, March and April, where we have our peak wind speeds, that is a shoulder season here, and our temperatures are pretty mild, and we really don't see a lot of heating and cooling load. So that really doesn't correlate well with our peak building demand, which will be more in the middle of summer. But as I said earlier, this is really just a small supplementation to the main electric service. And so since this system will be providing a very small amount of our total use, correlating it to the peak building use really doesn't do us any good. This graph is another one output by Windographer, and this is a probability histogram that shows the frequency at which various wind speeds are going to be seen. So this can give you a rough idea in terms of percent, and also a visual representation of, how often am I going to see 4 meters per second wind speed or 5 or 6 meters per second. And what you can see from this is that we are pretty low on our average wind speeds. We are predominantly in the 3 to 6 meters per second range. And if we go back to our power curves, these turbines really don't start producing power until 2.5 or 3 meters per second. So we're largely going to be on the lower end of this curve. But where that's useful is now we can look at these turbines and say which one is going to give us the best bang for our buck in terms of performance. And that brings us to this calculation, which we use to determine what our estimated electric output will be for each of those turbines. So this is a lot of data, but the big idea is we take that probability histogram and we correlate that into, okay, how many hours a year am I going to see 3 meters per second wind speed, or 4 or 5, and then if we take those hours, multiply it by the rated power output of each turbine at that wind speed, and then account for some adjustments for our air density at 2,000 feet, as well as some inverter efficiency and other system losses, and we can come up with an output at each wind speed over the year. And what that comes down to is, here at the bottom, we can see from left to right, we're going to see increasing performance with around 8,000 kWh with the vertical axis turbine, a little more for the Excel 10 at about 8,300, and we're going to see easily the most output out of the Advanced Wind R9000s. Now with the solar irradiation and estimated energy output of a solar array, that's a much more simpler calculation than for the wind turbine system. So we calculated the output using NREL's PV watts calculator, and that determines monthly kWh output based on the array size, which in this case is 10 kW, our location, which is Spokane, Washington, system losses, etc. And so here's what PV watts had calculated for us. So it calculates the monthly energy use, and it all sums up to a little under 13,000 kWh per year for our solar array system. Now, after looking at all this data, it's very clear Spokane, Washington is not a high potential area for wind or solar energy. But depending on the turbine, a solar array could output as much as 62% more energy than a similarly rated wind system. Now, we're not talking about a huge amount of energy, but just that 62%, that's a big difference, and it really tells you that, at least in terms of performance, the solar system is going to be the clear winner. So let's move on to environmental impacts. So with the wind turbine, we pulled a list of species of concern from the website for the Washington Department of Fish and Wildlife, and we identified that in Washington state there are 12 species that are considered endangered and 5 species that are considered threatened. And this is on either a state or a federal level. Now, it's with their website, we are not able to filter by county or city. So as far as our specific site, it's very difficult to say which of these 17 species are we actually in danger of harming with our wind turbine. So if we were going to go down the path of installing a wind turbine, it would be wise to hire a local expert prior to building. As far as the solar array is concerned, there's really not a lot of issues as far as threats to wildlife after this is installed. This is going to be a passive system. There's no moving parts. There's really no threat at all to any wildlife. However, as far as making the solar cells, there are some environmental concerns there. As far as the caustic chemicals and the water use that's required to make the cells, and the regulations are going to vary by country depending on where the cells are manufactured. And modules made in the US or Europe are going to have much less environmental impact than those made in China. Some studies say the impact is about half. So that is a definite concern. So let's move into permitting. For the wind turbine, our primary resource was the Washington Wind Energy Permit Toolkit, which is available online. And according to their classification, this would be a size 1 turbine, as it is less than 100 kilowatts, and its primary purpose is to supplement the electric utility of a building. So this matrix here tells you, what's permitted use, what's conditional use, and what is not allowed. So for a size 1 turbine in a commercial application, you can see that that is a permitted use. And what that means is really the only things that are required are standard building and electrical permits for the work. And it also means that there are no requirements as far as public hearings go in order to install your turbine. There are some setback requirements, and they measure it in terms of multiples of the wind turbine height. So if your wind turbine is 20 meters tall, then you need to have a 20-meter setback distance from property lines. And there are some concerns as far as if we were to locate the turbine along the west side near the river, and whether or not we would actually meet this setback requirement, or if the city would consider the shoreline a property line or not. So that is something that would have to be approved by the city if we did want to place the turbine there. We also input our coordinates into the FAA build-out display, and what this does is identifies other turbines that are installed in your area, as well as identify any areas that are definite no construction zones that are identified in red or possibly yellow as kind of a conditional use. And so there's no red or yellow identified, so we should be good as far as the FAA is concerned. So in summary, we do have some potential siting concerns if located on the ground, but otherwise just standard permits. If we do put it on the roof, then we will need to do a structural review, because the turbine is going to be adding a significant bending moment, as well as just the raw equipment weight on the roof. And there is a chance that after that review, we may have to make some upgrades, which are going to add to the project cost. And looking at a solar array, again, this is much simpler. We're not dealing with any large structures. This is passive equipment without any moving parts, no threats to wildlife. So standard building and electrical permits are going to apply. But if we put it on the roof, again, we're going to have to do a structural review and possibly upgrade the structure to support this additional weight. But because the load of a solar array is much more evenly distributed, and it's not contributing a large bending moment on the structure as a wind turbine would, I think the chance of requiring structural upgrades are much lower with the solar array than with a wind system. So with all these things we've considered, we're going to select one turbine and one solar array to be used for a final analysis. So for the wind turbine, we're going to go with the Advanced Wind R9000s. So as we saw earlier, the R9000s are going to put out significantly more energy output at the lower wind speeds that we're going to see in Spokane. By going with two smaller turbines, we're more likely to be able to install it on the roof, which alleviates a lot of our siting concerns with installing on the ground. And this is a reputable company, which is important, because the R9000 does not offer the same warranty or equipment life as the Berge Excel 10, but because it is a reputable company, you know it's a quality product. For the solar system, we're going to go with the 250 watt gigawatt panels with the polycrystalline cells. So the big kicker here was it's made in the USA, so there's less of an environmental impact concern, because besides that, these were identical to the Renesola panels. And we also have ample roof area, which means we don't need to go with the monocrystalline panels that the SunPower panels used, which would be useful if we had a really tight roof, but we still wanted to maximize our watts per meter squared. But since we have plenty of roof area, we can keep our cost per watt down significantly by going with the polycrystalline panels. So moving into the financial piece. So let's start with the available incentives. So DesireUSA.org is a large database which allows users to log on and easily filter available incentives based on things like technology or state or any other criteria. So the incentives we're going to look at or that are applicable to our project, there's the Business Energy Investment Tax Credit, and this is the big one. This is a tax credit equal to 30% of all expenditures that will come back dollar for dollar to the company. Right now it is applicable to both systems. However, small wind systems are no longer going to be applicable after 2016. So there is a good chance that this credit would not apply to our wind system unless we could, get this installed in the next few months. The second incentive is the Renewable Energy Sales and Use Tax exemption, and for a solar system, this exempts 100% of the sales tax, and for a wind system, it's 75%. And the last one is a Modified Accelerated Cost Recovery System, or MACRS. This allows a 50% bonus depreciation on renewable properties. Now, as far as a detailed economic analysis, all of these incentives were factored in except that MACRS incentive. To apply the MACRS incentive would require me to dive into McKinstry's tax returns, and the complexity is a bit outside of my knowledge, but it should be noted that that incentive is still available. For our energy cost, Avista Utilities provides electricity to our building, and they charge 7.4 cents per kWh year-round. There are no seasonal changes there. And very importantly, all of these costs I'm about to show you are estimates only. And if we really want to dial in the price, we're going to have to involve some contractors. So here's our estimated first cost for a wind system. The biggest component is the wind turbines themselves, which I've estimated at $22,000. I did try to get in touch with Advanced Wind, but they were not responsive when I requested a quote. And then we show the inverter, the controller and interface, towers, etc., and all the installation costs. We do account for the 75% sales tax exemption as well as the 30% investment tax credit. And our final total estimated cost comes out to $36,054. We took this initial cost and our expected energy savings per year and created a pro forma financial model which accounts for a 1.5% escalation rate, so we can see what is our capital cost of this project cumulative over the year and accounting for inflation. And what's really key about this model is we can see at what year are we going to break even. And in this case, it's going to be somewhere in between year 36 and 37. Here's our estimated cost for our solar system. Most of these costs were based on a estimated cost per watt, which were provided by Marina Gonzalez. Our panels and our inverter, those costs were easily found online. So again, the sales tax is exempted. In this case, 100% exempted, and the tax credit is applied, and we end up with a total estimated cost of $23,398. Again, we have a pro forma model. This one only goes up to year 25, as that is the expected life of the solar panels. One thing of note is these panels do have a performance degradation where at year 25 they're only going to put out about 80% of their rated output, and from when you first install them to year 25 it will have a linear degradation between those two values, and so that was accounted for in this model. And you can see here the break-even point is right between years 23 and 24. So here's a comparison of some key financial criteria for both projects. So we can see the solar array has a much lower cost. The energy savings are also a bit larger. Both projects will break even at one point, and the wind turbine does show a larger return on investment, but there's a couple caveats there. One is we assumed a 40-year life, which is pretty aggressive considering the manufacturer only specifies a minimum 20-year equipment life with inspections. And additionally, this is assuming that we can take that 30% tax credit this year, which is probably not very likely. So the chance of that system seeing a positive return on investment at all is pretty unlikely. Compared to the solar array, which has a positive return of a little over $2,000, which isn't much, but the break-even year at least falls within the life of that equipment. So we would feel a little more confident that that positive return would actually be seen. So let's close it out with a few other minor considerations. So aesthetics can be kind of a big deal to some people. So if we were to install these systems on the roof, they would have a pretty high visibility to people getting off the I-90 freeway exit, and it would really draw attention to our building and to McKinstry and get people talking and thinking about who we are and what we do. Some people, though, might consider wind turbines to be a little more impressive just due to their physical size. I mean, they're large, imposing structures, and a 25-meter tall wind turbine is really going to draw some attention to the building. But ultimately, this is a subjective thing, but it is something to consider. The other thing is maintenance and operation. So the wind turbines, they do require some maintenance because there are a lot of mechanical components and moving parts, and there are parts and labor costs associated with that. We didn't account for those in the economic analysis, but it is something to keep in mind. Compared to a solar array, which is a passive system, it might require some cleaning of the panels every once in a while, but that's a relatively minor labor cost. So getting to our final recommendation. So we've shown that both systems have a poor return on investment. And this is largely caused by the low wind and solar energy potential, as well as our relatively low electric rates. So on the merits of economics alone, this really doesn't make sense for either system, really. But remember, the purpose of this system is to showcase our support of sustainable practices. This isn't necessarily about the money for us. So assuming that that is our goal, based on what we've found, we're going to recommend that the solar array be installed. There's likely going to be an easier permitting process. It's going to be significantly less expensive with better savings, positive return, lower maintenance burden, and finally, there is a lower chance of environmental impact on the wildlife. So the solar array really wins in just about every category. And that's not to say the wind turbine doesn't have some potential advantages. It does have a longer equipment life than the solar array. I mean, some of these wind turbines are expected to last up to 50 years potentially. And to some, it may have preferable aesthetics. And maybe that alone is worth, the negative return on investment. Maybe we just want that to be a symbol of sustainable practices as opposed to something that's actually going to make us some money. But in the end, we are going to make the recommendation that the solar array be installed. So that's it for me. Thank you for your time. If you have any questions, feel free to shoot me an email. Thank you.